So first of all, I want to say thank you to the CIE organization for giving me this opportunity to be here. It's a privilege for me to talk to you. So I'm going to try something and try not to screw this up. So Raymond, tell me if I've got this right. I'm going to say, 下午好，亲爱的朋友们。Now that I've got the most difficult portion of my talk out of the way, I can go through the rest of it. So the reason I'm here is I'm really excited to talk to you guys about a big change that's going on around us. And the big change that is going on around us is so big that it is going to change our lives. It's already doing that. You know, a lot of industries that exist today are going to be transformed in ways that we will not be able to recognize them moving forward. Also will give a lot of the folks life-changing opportunities, both at a philosophical level, but also at a very practical level. As you think about your jobs and your next careers, there are going to be some amazing opportunities ahead of us. So, what is this big change that I'm going to talk about, and what is it that this is all about? It is similar in philosophy to some trends that have happened in the past. For example, when the world moved from mainframe computers and mini computers to personal computer, a huge set of changes have happened. Right? People may not remember, but mainframe computers used to take space as big as this conference hall, right? From there we went to personal computers, which are much, much tinier. And then came a big wave where personal computers then got replaced by cell phones in many applications, right? You went from, maybe millions of units of PCs to billions of units of cell phones. A similar revolution, if not bigger, is happening as we speak. We are in the very early stages. So this change is all about how we do computation. What kind of devices are we going to be using to process data that is required for the next generation of these explosive applications that are coming to us? So this talk is about trying to tell you about that change and how those changes are going to impact jobs and careers as we move forward. So, because it's an engineering audience, I'm going to keep the first part of the presentation relatively quick to tell you about some trends, but I actually have an engineering example to show you what sort of these changes would be and what sort of computation is going to be done and what architectures are going to be useful in the future. And the last portion of the talk is really talking about how careers are going to be impacted by that. Okay? So, really to get you guys motivated by what is driving all of these changes, I want to start with a little bit of an understanding of what applications are driving this. The previous talk that Titan gave is an example of an area that is driving a tremendous amount of computation, which is healthcare and drug discovery. But there are many such applications. So what I want to do is show you guys a small video of small companies that are emerging. These are not the giant companies yet, but these are companies that are building pretty innovative product with next generations of applications that Xilinx as a company we have visibility into. So I put together, it's a short 2-minute clip to get you guys oriented with these applications. So for some reason I don't get the audio. Is there any chance I can get the audio? And if not, that's fine. We can continue forward.
Audio is fine, so maybe continue and we can
Okay.
come back to the video portion.
That sounds fine. Yeah, it's not a big deal. And I will, talk to you guys about it. So this is a company that's specializing in machine learning applications for factory automation, industrial automation. This is a company called DeFi-Tech that does artificial learning applications for various applications in robotics, virtual reality, drones. It's another company that is doing image processing 4K video, 8K video, high definition video processing. This is a company that's specializing in developing software for autonomous driving. And this is a company that is developing applications that are based on eye tracking. So you use gestures and eye motion to take actions. This is a company that's in the communication space that's using LED-based lighting to provide a Wi-Fi-like service.
To guard Wi-Fi technologies. Typical cybersecurity solutions today takes 200 days. PFP detects and remediates in milliseconds.
Zerotech is one of the first batch users of our products. They're the second largest drone company in China. For now, they're building AI drones with our products, so we integrate a Zinc device inside for embedded vision, for object detection, pedestrian detection, and gesture recognition.
A big part of what we're doing here at Aperi is trying to bring a lot of these sort of large-scale practices from the cloud and from higher-level software development into sort of a contiguous pipeline from like the IP core vendor to the delivery of the product as an application.
At Drone Robotics, we're finding the partnership with Xilinx to be very interesting because we have a software platform that is modular and is capable, and we see that same kind of capability in the Zinc MPSoC, which has the dynamic ability to apply machine learning functionality or techniques in a modular and flexible way that suits our software platform.
Okay, so what you saw is, a variety of applications, right? And, I have videos that go for many hours with these applications. But underneath all of these applications are some big trends that are driving things. So I want to touch upon those big trends before moving on to the core of the talk. So the first big trend I want to point to is 5G. This is pretty real. You can argue, is it coming in 1 year or 2 years or 3 years? When is it really going to transition over from the current generation of networks? But 5G is a fantastic next generation network advancements. Huge benefits on many vectors, 1000x the network capacity, lots of benefits with respect to the aggregated number of devices, the latencies and so on. To one example, 5G people wonder what does it mean for me, right? You might be able to download an entire high definition movie in 1 or 2 seconds, right? That's the type of network capacity that you will have at your disposal. The next big trend I want to point to is video and vision. Lots of video is getting generated across the board, whether it's your home, whether it's your car, whether it's a factory, whether it's an industry, whether it's a city. Video is getting collected at phenomenal rates. In fact, there's a study that Cisco has published that says that in the next few years, every second 1 million minutes of video will be crossing the network or something like that. And it's just unfathomable, right? The amount of video traffic that is there. So things to think about is, what's going to happen when all this video needs to be processed, analyzed, stored, and, taken action upon. The next one is industrial IoT. This is where a number of things are getting connected to the internet is just exploding. If you think about it, the number of cell phones is of the order of billions, but the number of things that are going to be connected to the internet, people say the estimates are going to be in the tens of billions. So think about tens of billions of things that are going to be connected to the internet, and all of them generating some form of data that is needing to be processed to take actions around it. Where are these things coming from? These are things coming from smart factories, smart cities, healthcare applications, even walls like this in buildings, right, where you have sensors to say that is the wall mechanically being stable, can you take any action around it? So huge amounts of data that's getting generated from all these places. Now all of this data that is getting generated and collected from these various sources is getting aggregated and processed in what are called clouds. Cloud computing is a fantastic and high growth trend that is for real. Many markets are already taking advantage of it. In fact, tying back to the previous presentation, a hugely capable as well as potentially game-changing application is in drug discovery, right? For example, things like genomes and finding specific disease patterns in genomes. If you apply some of the techniques that are being applied in the cloud, you can sequence things in the order of days as opposed to weeks or months that it used to take before. So those are the sorts of applications that are fundamentally making a huge difference. So again, I don't want to bore you guys with a lot of trends in the cloud and these sorts of things, but these are all real trends that are happening. So now, if you think about what is powering all of this underneath it, in the end, there is actually a device or a set of devices that is powering all of this happening. Usually it's a semiconductor chip, right? So the question that we have to ask is, are the same types of chips and devices that we have used in the past going to be enough to be able to address the needs that are coming out of these next generation sets of applications? And that's the gist of the rest of the talk. We're going to see what those are. So first, let us ask the question, if I have a next generation application, let's say an image processing application, what sort of device would I need to solve this problem? So the types of things that those that are in the semiconductor industry we think about, and again, I don't need you guys to read through all this, are first things, how much expensive is this solution going to be? Is it a $1 solution, $10 solution, and a $100 solution? What is the performance required by this solution? Do you need to process 4K video or 8K video? Is it 50 frames per second, 1 frame per second? What is the power? Is it going to be on a battery? Do you need to last for 2 days, 10 days? How secure do you want it to be? Is it okay for everybody to have access to this, or do you have a privileged mode that you need to put in? How safe do you want it to be, right? If you are in a car, you don't want the chip to ever make a mistake. So a lot of the chips that we do today have redundant functions, right? You have a chip that basically computes one thing, and then after some time, the same thing gets computed by a different way, in another way, and then you compare the results. Only if those results match, then you actually go and take an action around it. So what are those sorts of things? So a whole host of things go into the solution consideration. The solution space itself has many options. You can use CPUs. You can buy a computer from off the shelf and try to solve the problem by writing some software on it. You can actually, on the other extreme, build a custom chip for your application. If you know exactly the type of application and you have a large enough market, then you will actually build a chip for it, because it's usually the best way to solve a problem. And then there's a whole host of other options in the middle, and I want to give you a classification of what these options look like. So this chart is a pretty simplistic way of classifying all these solutions. On the vertical axis is the efficiencies that you can get for the solution. And on the horizontal axis is the effort that it requires to actually make this solution. So fundamentally, at the bottom left are what we call as general purpose architectures. This is, you design a CPU, and usually on that computer, you can write an image processing algorithm, you can do some kind of a drone type of algorithm, you can actually do a healthcare application on it. So it's a very general purpose platform that you can build. We all program using C on a computer, so that's what you would think as a general purpose thing. On the other extreme, you can actually build a custom chip, right? A specific chip that can take a specific type of sensor data and can do a specific thing and produce a decision at the end. That's another way of taking the data and computing it. So that's the two extremes. What I'm going to argue and submit to you guys as a thesis for today is that there is a class of architectures in the middle, which are called as adaptable architectures, that we believe are going to be increasingly suitable and necessary to solve these next generation problems. So what is an adaptable architecture? Basically, an adaptable architecture is when you build a chip that you can still program in hardware, and the same chip can then be used for doing different applications, whether it's an image processing application or whether it's some kind of healthcare application or a security application. The same chip can be programmed and it can adapt to the end application. And FPGAs, for those that may be familiar with it, are a class of adaptable architectures. So I'm going to give you a sense for what these architectures look like and how, with a real example, you can see the benefits these architectures are able to provide for you. Before we do that, I want to take a minute to say, how many of you guys have heard about Moore's Law? Great, quite a few people. It's an engineering audience, no surprise there. So what I want to do is actually give you a little bit of thing about what's going on in the technology evolution and how each of these solutions are impacted by how technology is progressing. So this is actually the picture from Gordon Moore's original paper in 1965, right? What you see here are, a few dots based on what they were able to achieve at the time. The chart is showing the fundamental thesis of Moore's law, which is every 2 years or so, you are able to double the capability of what is there in your integrated circuit solution. And if you look at it, it's a pretty bold prediction based on just a few data points at the time. But the semiconductor industry has done pretty amazingly well over like 40, 50 years to be able to keep this trend going. But the reality is today, this law is definitely slowing down. If it hasn't stopped in some industries, it's definitely slowing down. So how do you react to some of this is part of the reason why these next generation applications require a different type of solution, not a traditional solution. So let's look at what's happening to each of the options that we had before. First, let's look at general purpose hardware. This is a study that was published out of Stanford University some years back, and it's a very nice chart that shows the capability of general purpose hardware systems and how they have scaled over the last 40 years or so. So all of these charts are useful, but I'm going to pick one, the blue chart here. This is really how single-threaded performance has increased. So what you see is over year, performance has kept on increasing, and people have gone from 100 megahertz to 200 megahertz to 400 megahertz to 2 gigahertz CPUs, and you keep getting additional performance. But interestingly, over the last 7 to 10 years, this trend has slowed down. You're not getting faster and faster CPUs. For many reasons, power being one of them, but for many reasons, this scaling has slowed down. Now let's look at the other extreme. Why not go ahead and build a custom chip, right? Because obviously that is the best solution that you can get. The problem with trying to build a custom solution is because of Moore's law and because of the complexities that are increasing, it is becoming incredibly expensive to build a custom chip. So what I have here is approximately what size of market you need to have to be able to build a custom chip. So you start at 65 nanometer, 40 nanometer and go all the way to 60 nanometer. You'll see that for 60 nanometer, the costs associated with building this chip mean that the market that you need to have needs to be over $3 billion, right? So how many markets are there where you can have this kind of capability? So the two extremes are general purpose hardware is not scaling as well, whereas custom hardware is much more expensive. So that's where the adaptive solutions come in. So this is the very first FPGA. FPGA stands for Field Programmable Gate Array. It was our company that invented this 30 years back. This is a chip that you can program to adapt to different needs at different times. So at the time, of course, this was a very capable device. Today it's a very tiny device. Since that time, the capabilities of devices have increased a lot. You have 10,000 times more logic. It's gotten 10,000 times cheaper. You have not just logic, but you have memories. You have a whole bunch of other functionality. And if you look at a modern FPGA-based device, this is something that we created about 4 or 5 years back now, and it's available in the market. This device has a big SoC, so you can actually write software code on it. It has memory systems, it has transceivers, it has security features, it has safety features, it has power management features. It's a very, very capable device that you can program. All the time keeping in mind, the benefit is that it is not a fixed function device. It's not a special purpose device. You can take this chip, you can put it in an image processing application, you can do some more programming and put it in a different application. So it's a flexible type of chip that gives you that benefit. And then if you fast forward to 7 nanometer, just earlier this week, coincidentally, we had announced this platform called ACAP, Adaptive Compute Acceleration Platform. It's something that's going to be in the future. You will see that it's an incredibly powerful platform that should be able to service a number of these next generation application demands. So there's a lot of jargon that I've gone through. So what I want to do is, I want to take a very specific example and show you why these type of architectures are beneficial. So the specific example I want to take is one which I was going to call as edge detection. So if you're having a video feed coming in, you usually want to typically find out for various needs where the edges are in these videos. So as an example, you see the picture here. There is a video on the left hand side, and then you want to create the edges out of that. Find my laser here, point out. Yeah. this picture here has the original, and then this is the edges that you want to detect around it. The reason this is important is because, once you have the edges, then you can make a determination. Is it a person? Is it a car? Is it a dog? You'll be able to make those decisions. It's actually a very simple operation, and the way you detect an edge is you look at a pixel and you look at its neighborhood. If the neighborhood is different, then usually that's an edge. If the neighborhood is the same, then you're not finding an edge. Think about it, right? If you have a blue pixel next to a yellow pixel, then something is changed. There is an edge in between. If you have a blue pixel next to a blue pixel, it's the same thing going forward. So it's a simple operation, but it's computationally quite involved. So if you do this operation on a general purpose hardware, state of the art, you usually get maybe 2 frames per second. But if you're able to take an adaptable architecture and map this onto it, you will get a real video performance at 60 frames per second. And what I have here is a small video that actually shows this. So there are 3 clips. This is the original video of the bunny. Next, you will see the same thing processed for edge detection in a general purpose hardware, and then the same thing processed using an adaptable architecture. So that was the original one, and this is the one that is getting processed in software. You'll see, look for the apple. The apple has landed, but you don't see it landing. You miss that entire sequence. And the exact same thing then if you actually put it in hardware on an adaptable platform. You get a much more live video response, right? So this is a pretty real mapping of how things are and where the benefits you can get from this type of an architecture. So now, of course, I showed something simple. You can actually extend that to many sensors and real time and implement machine learning algorithms. So these sorts of applications are well serviced by this. So now you may ask, what does all of this mean for me? Right? What does this mean for my career? So I'd like to give you guys a couple of trends to think about as you think about how are all these things impacting my career. So the first trend is that these solutions are actually quite complex to build, and as a result require many levels of abstraction to be able to build. And what do I mean by that? You can look at it from this pyramid. At the base of this pyramid, right, is complex things like chips. You obviously need that. You need the devices, you need software to program the chips. But then above the base platforms, you require programming languages. If you guys have heard of things like CUDA, OpenCL, these are languages that you use to program these devices. And above that, you have libraries. These are software-defined kits and environments. And then above all of that, you have frameworks called things like Caffe or TensorFlow. These are frameworks that give you high-level programming methods by which you were able to implement these sorts of applications efficiently. So what does this mean from a job or a career point of view? Traditionally, a lot of jobs used to be at this level. You used to be able to create a chip, you used to be able to write RTL and so on. But then if you look at a company like Xilinx, we actually hire a lot more people in the higher levels of stack. And I don't think it's a Xilinx specific statement. I think that's very true these days. That if you think you want to expand your career and actually see some additional things, you should think of the whole pyramid and not necessarily think of the more traditional ways of doing things. So that's the first trend. But one big difference compared to, let's say, 5-7 years back is that we are doing a lot more software-oriented jobs as well. And within the software-oriented jobs, these are systems content jobs. For example, a machine learning type of an application developer that understands something or the other about hardware is a very, very valuable commodity, right? So my sort of observation that I want to convey to you is, think about what you're building as far as the solution goes, as opposed to having a point skill in one specific domain. It's always good to have the deep point skills, but it's also important to have skills that span the whole pyramid. I think that's probably the gist of the message that I want to leave as far as careers and future goes. With that, I'd like to conclude saying that from a timing point of view, I think it's a phenomenal time to be in this business, because it's a change that is occurring at a pretty phenomenal pace and giving so many different types of opportunities. And a lot of this is because of the tremendous amount of data that's driving all these applications, and the explosive demand that is created by all these applications. Bottom line, I think it's a pretty exciting time to be in this industry. If you can figure out how to sort of maybe tweak your skills a little bit and expand them to have a little bit more systems content and higher level of abstraction content, I think you'll have a fantastic career. Thank you.